Hey everyone, I am Tim. I'm the CTO of Radar. Radar is a geolocation infrastructure company. As part of that, we do a lot of geocoding and search at Radar. So my goal for this talk is to give you a little bit of a sneak peek of how we do that. This is about our geospatial database that we call HorizonDB, and this is a little bit under the hood of how it works. So, we're processing over 1 billion API calls a day as a company. This helps motivate why we wanted to create this search engine in the first place. Really low latency APIs, really high uptime requirements from our customers. When we're down, they're down. So this is kind of the motivation of why we created this infrastructure. So here you can see the overall infrastructure design of HorizonDB. So that big box in the middle there is Horizon. It is a single binary written in Rust. So everything you see in that big box is part of a single executable. I'll get into all these boxes, what they are and how they work. You can kind of see on the left-hand side there's our input query of 841 Broadway. That's the Radar office. And on the right-hand side, you can see the result of that search forward geocoding query, the record that we retrieved from Horizon. And in the middle is kind of how everything works. So in the beginning, and on the left-hand side there, you see there's sort of this query classification stage. We're using a few machine learning libraries to really understand the query. So we're using LightGBM from Microsoft and FastText from Meta to process the input and understand, is this query an address? Is this query a city? Is it something else? And that allows us to be smarter in this middle phase here where we do candidate retrieval. And so for that, we use these various fetchers for addresses or places or regions. So it allows us to just be a little smarter on which fetchers we run. If we have a lot of confidence in the classification of the query, sometimes we don't have a lot of confidence. We need to run multiple fetchers, but that query classification tagging stage just helps us kind of be smarter about what we fetch. After that, we would just rank the results and return them. So let's talk a little bit about some of the boxes inside here. So as I said, it's written in Rust. Why do we choose Rust? It's a systems programming language with a modern developer experience. It's got batteries included. It's got great tooling and dependency management. It's got a rich standard library. So there was a lot to like about Rust. It's efficient. There's no garbage collection. It's multi-threaded. It runs in a single process versus multi-process, and that turns out to be a big deal because when you need to load a lot of geospatial data all at once, you don't really want to be running a process per core. It's just going to be really inefficient. So that was really attractive as well. And then, it's got great C and C++ interfacing, so it allows us to leverage a bunch of great tooling like Google's S2 and Microsoft's, LightGBM. So that's kind of how we got to Rust. And then a little bit about LightGBM. So it's a decision tree library from Microsoft, gradient boosted, and it's really fast. So it's really fast to train and do inference at runtime. We use this to do query classification. So we can say, hey, if someone types in New York, hey, we kind of know that that's like probably a region, or a region or a few other things. But or if it's an address, we can kind of figure that out as well. And then we also use it to break apart the query and understand the different parts. So hey, 841 Broadway, it's actually like, hey, there's a primary number and an address. So we use LightGBM to help us crack open the query. We've trained it on our geocoding corpus, user queries, synthesized data, and things like that. We also leverage FastText in this first phase as well. It's a great word-to-vector library for Meta. And so it can actually represent, words as semantic vectors. So similar words will have similar, nearby vector values. One of the nice things about it versus word-to-vec is very popular, but one of the nice things about FastText is it can understand partial queries, like parts of words. It doesn't need an entire word to classify it. So that's really attractive when you're handling, auto-suggest, autocomplete style, requests from users typing something in a web browser and you don't have a full word yet. So that's really useful. So it's great for that. It's really fast, and we actually leverage, these embeddings as part of, the input to the like GBM step as well. So they kind of play well together, which is nice. Once we've classified the query, we say, hey, we kind of understand what it is. We think this looks like an address. We think this looks like a region or a point of interest. Then we can run the correct fetchers. And so there's a couple different ways we fetch data. So this one is probably the most interesting one. It's called an FST. There's a great FST library in Rust. FST stands for, it's kind of a mouthful, it stands for finite state transducer, which sounds complicated. But if you look at the diagram on the bottom, and you're thinking back to your computer science, like it probably looks to you like a finite state machine, and that's what it is with some bells and whistles. As we're kind of moving along the edges of this finite state machine, these edges kind of the arrows in the diagram, they represent characters of the input, right? So someone types in a query for 841 Broadway, we're storing that along these edges in this graph. And so as we move along through this, this FST, we're kind of getting to the end of, the end of the FST. And if we have a hit there and there's actually a record, there will be some metadata about that record. Most importantly, like the ID in the database of that record. So it's kind of just a search technique to quickly be able to process an input query and look up that record in the database. So it's got a lot of nice properties. It's a little tricky the first time you encounter. At least it was tricky for me. But it's a cool data structure. It's really useful for quickly processing queries. So that's the FST. That doesn't always work though, because sometimes people will input words out of order. That FST that I just talked about is really good at the happy path. So it's really good at queries that are really well formatted and normal. But as we all know, like a lot of queries don't look like that. So when we don't find anything with the FST, we fall back to using a library called Tantivy. Tantivy is really just Lucene, but for Rust. So it's a text processing library. It's got basic stuff like TF-IDF. It's really good for just just general search. So we fall back to that when we can't find anything in the FST, and that kind of gives us a bunch more coverage. And then finally, once we've used either this Tantivy search step or this FST lookup step, ideally one of those has found a bunch of candidate records, and so it'll have sort of database IDs associated with those results. And then we'll turn around and we will fetch those from RocksDB. RocksDB is a storage engine from Meta. It's a log structured merge tree, which just means it's really good at reads and writes. It's highly concurrent. It's important that obviously it's important for it to be fast at reads because we want low latency for our customers, but it's also really important for it to be fast at writes because when you want to ingest new data, new records, you don't want to have to sort of take your cluster offline or create a new cluster from scratch. You want to be able to write to that infrastructure as it's serving. That's a very nice property to be able to have. So those log structured merge trees are really good at that type of thing. Yeah, and so that's kind of our core storage layer for the data. So that's really it. Here's the sort of overall picture again. So just real quickly, just to go through it again. Kind of this query classification tagging stage using machine learning. Some popular libraries there, like GBM, fast text. doing the candidate retrieval with FSTs and Tantivity, and then looking up the data from RocksDB, and then just ranking that and producing an output. So I know that was a lot at once, but I hope everybody learned a little bit about geocoding and search, and just a sneak peek of how we think about it at Radar. Thanks.